All right, slope fields. So let's find the slope of the line tangent to a circle. Okay, so how do I find the slope of a tangent line? What's that another word for? Derivative. So take a derivative. Find a derivative of a circle centered at the origin with radius 5. Do you remember how to write the equation of a circle? Centered at the origin, radius 5.
X squared plus y
Equals radius squared. So there's our circle at the origin with radius 5. X squared plus y squared equals 25. Okay, but we want to find a derivative. We want to find dy dx so that we can get a slope of a tangent line. Oh, yes. Ambria, what's the derivative of 2x? Oh, I just gave away the answer. My brain is just pushes. Oh, I can push them back one. So I'll do the first one, 2x. Ambria, what's the derivative of y squared?
2y.
That's partially right. There's more to it, though.
Y.
Good. So 2y, and then either dy dx or y prime, either one. Ashlyn, how about the derivative of 25? 0. It's supposed to be the easy one, but sometimes people forget and just write 25 there, and then that messes them up. Okay, we're looking for y prime or dy dx, so now a little bit of algebra. So 2y prime equals negative 2x. I'm going to shift to dy dx, because that's how we usually do it in this unit, although y prime is the same. The 2's would go away, so negative x over y. So that would tell me the slope of a tangent line to that circle. I mean, we would need to know what coordinate we were at, but we would get the slope of the tangent line to that circle at whatever point. Would the equation be different for a circle centered at the origin with a different radius? So let's see, a different radius would have affected the 25. So how would that have changed our eventual dy dx answer? Yeah, here's where you're shaking your head. No, because whatever constant this is, the derivative would be 0, and then the rest of the problem would be the same. So no, radius wouldn't matter. We'd still have that as our dy dx. Okay, next up is this definition of a slope field. On a grid of points, we can draw short line segments. Sometimes I call them like slope pieces because they're slopes, but they're just little pieces of slope. They're not full-on tangent lines. They're just little slope pieces through each point with a slope of negative x over y. This would create a slope field. So we're going to construct the slope field on this graph for the derivative we just found. So 1, 2, 3, 4, 5. So that's 25 different problems we have to solve. But they go pretty quick. So let's see. And these are kind of fun because when you get to the end, they're usually symmetric or there's some pattern and it looks kind of cool. So that's also a bit of a check. If you get to the end and your slope fields or your slope pieces are like all over the place, then you probably did something wrong. If there's some sort of pattern to them, you probably did it right. In fact, we're not to those bottom set of graphs yet, but you can see that those are optical illusions, or there's at least some pattern going on to all of them. All right, so let's just pick, let's just start at negative 2, 2. We'll go point by point. Eventually you'll get faster, but let's start out nice and slow here. So at negative 2, 2, my slope is negative 2 over 2, so that would be 1. So my slope at negative 2, 2 is 1. So I'm going to do a little slope piece, and you can look down to see kind of what they look like. at negative 2, 2, I'm going to draw a slope of 1. Again, not the full line, just a little slope piece. Let's move left to right, so that would be at negative 1, 2. So dy dx would be negative 1 over 2, also known as 1/2. So how does the steepness of this slope compare to the one we just did? Half of it, yes. Less steep. It'd be nice if I had another point over here to sort of aim at 1/2, like up 1 over 2. So something like that. All right, my next point would be 0, 2. So that slope, what's a better way to say negative 0 over 2? 0. And what does a 0 slope look like? Yeah, horizontal. So that's an easy one to sketch in. Let's keep going. So 1, 2. That slope would be negative 1 over 2. So back to a half, but this time negative 1/2. I'm putting an extra point out here just to give me something to aim at so I can get my slope correct. So right, negative 1/2 is down 1 over 2. So if I really want to be accurate, I could lay out the 1/2 and then just do the little piece of it there. What about at 2, 2? What's my slope going to be? Negative 1. So a little bit steeper than that last one. I'm going to press pause and let you. What happens when we get to negative 2, 0? Undefined. But undefined doesn't mean like nothing's there. What does an undefined slope look like? A vertical line. In fact, that's an easy one, right? All of those have have a 0 in the bottom, so all of those are up and down, vertical. All right, so just be careful with the signs. Again, when you get through, you usually have some pattern. And usually if students mess up, they mess up one, and it becomes really obvious if like one of these is pointed, feels off from all the others, it's probably wrong, so go back and check it. Let's back up a second. Where did this slope come from? Like what equation did we start with, or what shape did we start with? A circle. What does that kind of look like? A circle. So even if we only started with dy dx, this gives us a picture of the solution. Slope field gives us a picture of, you know what, I should say solutions, plural, because we don't know what the radius is yet, but we can tell by looking that it's a circle. We don't know if the radius is 5 or 1 or 700, but the picture suggests the answer is a circle. So slope fields, when we graph them, like eventually we're going to combine slope fields with solving differential equations. We're not really there yet, but when we get there, separate, integrate, quantitate, like slope fields help us because now even before I start on the separate, integrate path, I'm pretty sure my answer is going to give me a circle. So slope fields are easy to do, just be careful, and they're helpful because they give you a picture of what your solution would be, an easy way to get a picture without, like you get a picture of the solution before you even have the equation. Okay, but that's a little bit later. Right now we're still worried about slope fields. So these are already done for us, but the things I want to notice, especially about those top two compared to each other, anything you would say or notice about just looking at those two? It's kind of an open-ended question. Go ahead, McKenna.
The number is the opposite sign of
Okay, I think you're saying when x equals 2, the slope is 0. Is that kind of what you're saying?
Yeah.
That's good. That will help us because finding the zeros is an easy way to start drawing your slope field. Is if you can figure out what makes the thing 0, that's a pretty easy start. And so instead of going like point by point, we'll start figuring out some shortcuts on these things. That same logic applies to this one. Whenever y equals -1, I kind of switched to m just because it's easier and shorter to write. The slope is 0, and so we see that on that line. So that's a good observation. Finding the zeros is a great way to identify. A lot of times these are matching problems where we either give you 4 graphs and 1 equation, or we give you 4 equations and 1 graph, and you got to match them up. One more thing I'd say about these two. That was the main thing. I guess there's 2 main things. That was one of the main things. The other is this one only depends on x. And you can get that from the equation. The equation only has x's in it. But you can also get it from the graph. It doesn't change, the slope doesn't change when you move up and down. Right? If you look at just one column of slopes, they're all the same. Right? It doesn't matter what y is, it only matters what x is. That slope only changes as you move left and right. You pick any column and all the slopes are the same because it only depends on x. And then a similar thing can be said for this one, only depends on y. Kind of the same thing. If you look across, so if you look as x changes, the slope doesn't change. You pick any x line and the slope is the same all the way across. But if you look up and down, well, it changes because it depends on y. So that's 2 of the main ways to help match up slope fields is where is it 0, because usually that's an easy thing to figure out. And then also, what does it depend on? Well, these 3rd and 4th ones are a little bit trickier. This is the one we just did, so I'll just say C above on that one. That's that negative x over y. But I would also say it depends on x and y. Right? It's kind of the same thing. If you look at a row of slopes, they're changing. If you focus in and look on a column of slopes, they're changing. It depends on x and y. We should have done what we did earlier. This was 0 at x equals 0. So even though it depends on both, whenever x is 0, we get a bunch of 0 slopes. Right, this last one also depends on x and y. Where is this one 0? Where is the slope 0 for this one? So I can set my slope equal to 0, and on this line y equals -x, the slope is 0. That was a little harder than the others, but you can still see those 0 slopes there on the line y equals -x. All right, back to this one. In the above slope field, sketch the solution curve. We haven't done that yet. Going through the point 0, -3. So let's start with 0, -3. Almost put that at the wrong spot. 0, -3. Okay, when sketching curves, you sort of just follow the path and do not cross slope field lines. Like everything should be like just kind of follow the path. This one looks sort of like a whirlpool, right? So we'll follow the path around. Starts out with a slope of 0, and then it changes a little bit. And just because I know this is a circle, I know it's gonna hit 3, 0 over here. 0, 3. This picture's not perfect, but there's my solution curve. That's one of the solutions to this differential equation. And again, it's a visual solution, not a equation solution. So we did equation solutions Monday and Tuesday where we separate and integrate. Now we have a bit of a shortcut on that. We've got a visual solution to our curve. And this last one, in the above slope field, sketch the solution curve through the point 4, 3. So 4, 1, 2, 3. So there's 4, 3. Okay, so looks pretty steep right here, and it's only getting steeper, so that looks like it's going way up. Less steep. One more, I guess, hint on sketching these solution curves is that you want to be parallel to the nearest slope field.
Wait, if it's 0, 3, is it going to be 3? Like, every direction?
Say that again? For this one? 0, -3? I mean, we happen to know this is a circle, so I know it's going to go through all the 3s. But if we didn't know that, we should still end up with something circular, but if it didn't hit all the 3s, that would be okay, because we're still working on things. And it's a visual hint, it's not an exact solution. By the way, all 3 of these things kind of say the same thing, like just follow the path, don't cross a slope field line, meaning be parallel to the closest slope field. So that's, I'm trying to do that on this one. Then this one makes a turn here, because when I hit y = -x, I have to be parallel. And I can't cross a slope field line, so this looks like this one's tricky because there's not a whole lot of information in there. It does something like that. And you look back and you see we didn't cross any slope fields. We ran parallel to them all. And if we hit one, it was only because we were going right along with it. Like right there we were pretty close, and right there we're pretty close. -1, -3. All right, why don't you try the slope field through -1, -3? If you got a different color, that might be helpful, but they end up on different sides of that, what looks to be an asymptote, so maybe you don't even need a different color. So there's the picture of the slope field, or the solution curve through -1, -3. Okay, again, most of these are going to be matching. So here's tips for reading a slope field, or maybe we should just say matching a slope field. It is nice on the AP test if you get a free response question with a slope field, because that's pretty easy. But you'll also get some matching slope field things. The only thing I would add to this list, I would put it first. It's the first thing that McKenna said earlier. So this is step 0. McKenna, what did you notice first when I asked for something to notice on that last slope field?
That the slope was 0 at the primary pool.
So we want to ask, where is the slope 0? That's usually a really good start on figuring out which slope field matches with who. So where is the slope 0? Tip number 1, although it's number 2 in our list because we started with 0, look at the slope along the axes, because on the axis x is 0 or y is 0, so it just makes the math really easy. So plug in x equals 0 and see what happens. Plug in y equals 0 and see what happens. Look to see if the slopes only depend on x, meaning that as you move left to right they change, but not as you move up and down. 3 is kind of similar. Look to see if they only depend on y. So if it only changes going up and down, but doesn't change left and right. Look to see where they're positive or where they're negative. And then lastly, units on the slope fields may be different. So be careful about, that's pretty rare, but if the scaling is off, be careful about that. It's usually close enough that that's not an issue. And I guess the last thing is if you're really stuck, you can just start plugging in points. That's kind of tedious, kind of a pain, but if you absolutely can't figure it out, then that's what you're left with. Okay, so matching on these 4. Let's see. Do we want to start with the equation or start with the slopes? I don't know. I guess let's start with the equation. Y over x. So where's that going to be 0? Where's the slope going to be 0? What would make y over x have a slope of 0? When y is 0. Okay, so let's look at our answers here. In fact, I'm going to do it this way because I'm going to process of elimination here. Let's see, when y is 0, I want a slope of 0. Does that happen for A? No, those look undefined, so A is out for this one. Does it happen for B? It's hard to tell, but maybe. C, same thing as B, hard to tell, but maybe. And then D, that slope is definitely not 0 when y is 0. Okay, so we're down to B and C here. Okay. At this point, especially since I'm looking at there's different signs going on, let's just check the point 2, 2 and see what happens. So at 2, 2, my slope is 1. And I'm really looking at B and C. And it's hard to tell where 2, 2 is, but somewhere around there. 2, 2. Okay, I think I've got it figured out. Because one of those has a slope of 1, and one of them has a slope of negative something. So which answer am I picking? B, because B has a slope of 1. So let's see, the next one I'm choosing between A and C and D. I've got x over y. So where's the slope 0 for x over y? When what's 0?
X.
When x is 0. So let's see where that happens. Let's see, when x is 0, yeah, that works for A. B we already used. C, when x is 0, that looks like infinity, so that's out, or undefined. So maybe it's A or D. I'm going to press pause and let you finish matching those. Alright, question 2 is sort of the opposite problem. Well, I guess it's not the opposite problem, it's just which one of those equations matches the graph. And this one's kind of tricky because you look at your graph and it's like, well, it definitely looks like a sine or a cosine, but that's all my options, so I got to be careful here. Let's see what happens at x equals 0. That means I got to plug it in all of those. What happens on the graph when x is 0? What's the slope look like? 1. Definitely positive, probably 1. So let's see if I plug in 0 at x equals 0. What's the sign of 0? 0. So what does that mean about A and C? They're out because they didn't have a slope of 0 at 1. Let's see, what's the cosine of 0? So I think it's b, but we better make sure on d. What's the, oh yeah, negative cosine of 0 would be negative 1. So the only one that has a slope of 1 at 0 is b. And so I was worried I was going to have to worry about pi and pi over 2, but it didn't matter. As long as I figured out what was going on at 0, we were good. All right, number 3. Let's look at the equations first. 1 over x. So tell me something you notice about 1 over x. Before we even get to the graphs, tell me something that's going on there. Okay? When x is 0, the slope is undefined. So let's look for that first, and maybe that's enough. Maybe it'll narrow it down. Let's see. When x is 0, our slope is undefined. I think there's only one option. Careful, when x is 0, when x is 0, so we haven't gone anywhere left and right, those slopes are 1, those slopes are 0, those slopes are changing, so it has to be b. That's the only one where when x is 0, the slope is undefined. All right, I'm going to pause. Put those on tape for those at home. Okay, the only thing left is to combine what we did Monday and Tuesday with what we're doing today. And with only 5 minutes left, we're going to hold off on that. So today's assignment is going to be worksheet 2, but you can skip 2 and 5 because that has the combination of stuff with yesterday.